Good morning, everybody. Welcome to the second session of this year's NESSIS. This session is all about explorations in soccer, or football for the rest of us. The first speaker is Pete Philipson. He's a senior lecturer in statistics at Newcastle University in the UK and is the current chair of the Royal Statistical Society's Statistics in Sports section. He's a lifelong sports fan. He's particularly interested in applications involving count data, subject to both under and over dispersion. So, Pete?
Thank you very much. Hopefully everyone can hear me okay. Morning, everyone, and thanks for coming along. So yeah, as said, I'm going to talk a bit about, I've been coaching myself all week to say soccer, but forgive me if I lapse into football. So I'll try and say soccer. A slightly different take on it, and then I'm going to talk about yellow cards rather than goals, and just how we might think about modelling those, and in particular, whether referees exhibit any sort of bias across the Big Five European football leagues. And I'll talk about the data and what I mean by Big Five as I go along. So I've done two versions of this talk before, one which is longer, one which is shorter, so I'm hoping this one will settle at the right time in between, but yeah, I'll keep an eye on the clock and hopefully keep myself right. Talk's basically in three chunks, so I'll start off with some background and some exploratory data analysis to hopefully motivate the problem. I'm then going to talk about how I modeled the data, and then I'll present the results at the end. Okay, so background and EDA first. So I guess I was interested in a different take on football, so goals have been kind of studied to death, unsurprisingly, because it's the primary outcome of interest. I was looking at small counts at a similar sort of time. I was looking at a data set, I stumbled across the yellow card column, had a bit of a look at it, and it seemed to be something that was ripe for looking at under-dispersed count data. What I mean by under-dispersion is just that it's got less variability than you would expect if you made a usual Poisson assumption. So the variance essentially is smaller than the mean. So yellow cards are issued, basically if you didn't know this, for a moderate disciplinary infraction. So if you do something wrong that it's not hugely wrong, you might get a yellow card from the referee. And if you get two yellow cards, you get a red card and be sent off from the pitch. And if you did a major disciplinary infraction, you would jump the yellow card and go straight to a red card. So there's not much work been done on yellow cards, probably for the reasons I said before. So people are interested in goals, because that's how you win games. But yellow cards has been studied a little bit. So one bit of work used a bivariate Poisson model and a negative binomial model. But they basically gave a tariff to a yellow card and a red card and studied the number of disciplinary points the team would get rather than the actual raw counts themselves. And another bit of work basically used the number of yellow cards as a covariate to model the probability of victory in a Bundesliga match. And the first of these papers found some evidence of refereeing bias in the English Premier League around 20 years ago. And in the second paper, they found that accruing more yellow cards diminishes your chance of victory. So, which kind of makes sense again, especially if those yellow cards lead to a red card. So a bit about the referee. So I'm a regular soccer goer in the UK. So I'm a Newcastle United fan for my sins. Haven't seen a trophy. I'm currently 44. Don't know when that's going to change, but we live in hope. So in soccer, the referee's got a bit of a thankless task. So I just picked out a couple of quotes from one from a very famous English manager in the 60s, Bill Shankly, who managed Liverpool, and essentially said the trouble with referees is that they know the rules, but they do not know the game. So essentially, he was saying they interpret things, but don't have a feel for what's going on. And secondly, from a book called Calcio by John Foote, it's all about the history of Italian football. He said Italian referees can be compared to sheriffs in the Wild West, trying to impose the increasingly flimsy authority of law and order in the face of mistrust, hostility, and violence. And lastly, so this is a game. It's called Mia Kappa, I think. It was created by the president of Como. So Como, at the time, were a team in the top flight of Italian football. Their president was Enrico Preziosi. He was also a toy maker. He made his money in toys. And he was so outraged during the course of a season that through a series of decisions that went against Como, penalties, late goals, things like that, that he commissioned a game that essentially was whack-a-mole, but with referees. It was wildly popular in Italy until it was kind of forcibly withdrawn a year later. I think you can still find rogue copies on eBay. But kind of that's where we're at with referees in Italy, especially, but also the rest of the world, I think. And it's pretty ubiquitous across sports that the referee has a somewhat thankless task. Okay, so for this particular application, I'm going to look at data from the Big Five men's European football leagues. Big Five isn't the name I came up with. It's a name that, I don't really like Big Fives and Big Sixes and et cetera, and Big Fours and Big Threes in tennis, but they're an easy way to navigate things, so we'll stick with it this time. And I basically had to draw the line somewhere for this data. So Big Five in terms of men's football in Europe means the English Premier League, the French First Division, and the top flights also in Spain, Germany, and Italy. And I've got data across 4 seasons, although I've actually got 22, 23 now, so that's slightly out of date, but nevertheless, 4 or 5 seasons worth of data. And this gives around 7,500 matches, but each of those got a pair of observations, so the yellow cards for the home team and the yellow cards for the away team at the same time. And we have about 130 teams and about 170 referees. And nicely, because of this time span, so not nice that it happened, but at least there's some upside, is we've got data both before, during, and after the impact of COVID-19. So one of the covariates I'll think about later on is whether the number of yellow cards varied when games were played behind closed doors. So the data on yellow cards, as a lot of football data is and sports data in general, are publicly available. You also get the referee name. In the case of the EPL, the English Premier League only, they're publicly available at this website here. And the data on the referees and the attendance are publicly available at this website here, FBref. And these two things can be basically combined in a fun data wrangling exercise. Sometimes the teams have got slightly different names, so sometimes it's a native name and sometimes it isn't. So that was a fun rabbit hole to go down for a few hours on a Monday morning, but taken care of now, thankfully. So what did I find when I did a bit of exploratory analysis for these data? So basically, by each league, we can work out the mean and the variance. So here I'm forgetting about home yellow cards and away yellow cards, just looking at it as an overall value. And in each case, the point here is that the mean, which is this number here, exceeds the variance in each case. And when the variance is less than the mean, we basically have something called underdispersion. And it means that the standard approaches you might take, like a Poisson model or a negative binomial model, won't work very well because they only handle equidispersed data or when the variance exceeds the mean, so the opposite problem. So it looks like we've got some underdispersion at play, so I need to think about that when I'm building a model. This obviously ignores the effect of covariates, but what normally happens is as you add covariates, you reduce the variability. So if anything, when you've got overdispersion, you might be conscious that you've omitted things in your model, and then adding in those covariates will soak up that extra variability. That's probably not going to happen here, but it will allow for covariates anyway. But it looks like underdispersion is a real phenomenon for these data, so it might be something I want to consider. And the other thing I was thinking about was, so referees are expected to be alike, so the governing bodies in each country want the referees to be as homogeneous as possible. Yeah? Whereas teams we expect to differ because they have different characteristics, different playing styles, different managers, et cetera, et cetera. So is it the case that the referees are as different as the teams, or are the referees somewhat more similar, which is what ideally football associations would want? Okay, so at the referee level, we can basically plot the mean number of yellow cards, the variance against the mean for each referee. The size of these dots, a slightly bigger dot means I've got more data for the referee. This dashed red line essentially is a line of equidispersion, so then the variance will be the same as the mean. And for anything below that red line, where most of these points are, that means that the variance is smaller than the mean, so we've got underdispersed data. So it looks like each referee has got a mean that's bigger than the variability. And I guess what that means in real terms is that they might give around 2 or 3 yellow cards, and they're very consistent about that number. Yeah. The other thing to think about, because I've got these pair of observations, so home yellow cards and away yellow cards, the easiest thing to do to model these is if they're independent, which is what I did first, until an annoying colleague said, have you thought about the dependence? And then I had to do a lot more work to get the model to accommodate this. So I basically worked out something called Kendall's Tor B, which is just a measure of correlation when you've got discrete or ordinal data. It accounts for ties, and if we do that for each league separately, we get a small but modest kind of positive association. It's very significant because of the amount of data that we've got, I guess. But it looks like there might be some modest positive association between the home yellow cards and the away yellow cards. So we might want to factor that into the model as well. And one way of exploring the dependency is to basically look at the joint distribution of these counts, so look at the home and aways together in the data set and just basically formulate that kind of table of probabilities, and then work out the distribution of the home yellow cards and the away yellow cards, and then just under independence, so just multiply the home by the away and divide by the total, like a chi-squared. We can see, and then take the ratio of these two things, we can see that basically any number bigger than 1 here says I've got a ratio where the joint distribution says that there's more yellow cards than I would expect under independence. So on the diagonal here, in this bottom right bit, essentially in the real data, we see more situations where both teams get quite a few yellow cards than we'd expect if the distribution was if they were independently issued. Likewise up here, so we get more where we get no yellow cards at all, so a very quiet, mundane game. We get twice as many of those situations than we'd expect under independence. And on the off diagonal, we see the converse. I guess this excess has got to go somewhere else. And we see that we very rarely get situations where one team gets a lot of yellow cards and the other ones don't. So I guess what we really see is a lot of situations where nothing happens, and then a lot of situations where a lot happens, and it involves both teams. And we don't usually see a game that's really lopsided in terms of a lot of yellow cards for one team and not for the other team, which might be what we expect if we think about it. Okay, so that leads me to modeling the data. So what I want is to conduct an analysis that properly accounts for the dependence between home and away yellow cards, and also to use an appropriate distribution to model these things. So that means I want a bivariate count data regression model, which accounts for hopefully under-dispersion, but might also want to allow for over-dispersion too. So a flexible model that allows for all of these things. And I want standard inferences for the covariates. So I want to say the normal things like we can in a Poisson-type model or a negative binomial, because that's what people are used to. And I'd also like it to be routinely implemented. So it's all very well coming up with a fancy model, but I need to be able to do it in practice in kind of relatively short order. As for the model itself, so forgetting about the distribution, we might want to think about the covariates. So what I want is to have individual, i.e. referee level effects for the mean and maybe also for the dispersion. I want to also model the team level effects. So that's number 4 here. As kind of common across all sports, I might want to model the effect of being at home. So is there a home advantage? Do home teams get fewer yellow cards? Also want to look whether the absence of fans due to COVID-19 made a difference to the number of cards shown. And also the interaction between these two things. Yeah, so during the pandemic, did it change? If there was a home advantage, did that disappear? Or did that get bigger when games were played behind closed doors? Differences between leagues as well. It's got these 5 leagues, and we'll see if there's any differences between them. And also any changes over time. So usually at the start of most seasons, there's new initiatives to crack down on a certain type of play or a certain, like shirt pulling, I think was a case in point a few years ago. Does that lead to a sudden excess of yellow cards before things settle down again? So I've also got a temporal component to the model. So that led me to something called the Conway-Maxwell-Poisson distribution. Well, that's a slight lie. I'd already seen the distribution for another application, but I thought, okay, it might be useful again here. So most count distributions were developed to handle the more common overdispersion. So it stands to reason. Overdispersion is more common in general, so there's been more attention paid to it. But the Conway-Maxwell-Poisson distribution basically generalizes the Poisson with an extra parameter that allows us to have both over or underdispersion within the same model, which I will refer to as bidispersion. So you allow both of these things within the same model, which is quite a neat property. And it was first introduced around 60 years ago in the context of queuing, and then it kind of lay dormant for a long time, but then it's had a lot more traction in the last kind of 20 years. So why does handling bidispersion matter? So why can't I just go ahead and fit a Poisson model here? Well, I would argue that the Poisson model is too liberal when you have overdispersion, so it underestimates your standard errors, so you get false significance. So that's typically sorted out by using a negative binomial model, where you then get the correct inference. But if you have both types of dispersion, then the Poisson model will be conservative, but it'll also be liberal within the same model. So sometimes it'll be saying things are significant when they shouldn't be, and sometimes it'll be saying the converse of that as well. So essentially, it'll mess up your inferences if you don't get the variability right. And a negative binomial model, as I explained earlier, that can only help with overdispersion. So a negative binomial model can only increase the variance in your model. It cannot decrease it. It's the way it's constructed. So it's at best the same as the Poisson when we've got underdispersion. So it doesn't look like that's going to do the job we want. So the Conway-Maxwell-Poisson distribution looks like this. So this is just its probability mass function. So this bit looks largely like a Poisson distribution. Then we have this normalizing constant to sort things out. The distance being we've got this parameter nu up here that distinguishes it from the Poisson. Yeah, it's got this extra parameter. So lambda is a rate parameter, so importantly it's not a mean parameter, and I'll come to that in a few slides' time. And nu models the dispersion. And like I say, this g term here is just some constant term that ensures you've got a proper distribution, i.e. the probability sum to 1, etc. And it turns out, it is always nice that several classic discrete distributions are special cases. So if this new parameter is equal to 1, obviously you'd recover the Poisson distribution. If it goes to 0, you get the geometric distribution, and as it goes to infinity, you get the Bernoulli distribution. So it means if we fit a CMP model, we can basically test whether we have Poissonian variance or not, so it's nested within the model. The problem is, though, the CMP distribution does not provide nice inferences, so it's a rate parameter lambda, so all I could say is that something increases the rate or decreases the rate, and I can't quantify it in the usual type of way, which is a bit unappealing. What we can do instead is reparameterize it in terms of the mean mu, so we can define a new parameter mu, which essentially is this infinite sum. We can rearrange that as an infinite order polynomial in lambda and nu. That means that lambda is an nth order polynomial that depends on the mu and the dispersion parameter. And under this reparameterization, we call this an MP-CMP, so mean parameterized Conway-Maxwell-Poisson distribution, or just CMP mu, if you prefer. So I've constructed a polynomial, but have I made things a lot harder computationally? Well, at first sight, yes, but there is some workarounds we can do. So a chap called Alan Huang first said you can use a bisection and Newton-Raphson approach to find lambda, given a certain mu and a certain nu. And this is applied in small sample Bayesian settings, but it's not particularly scalable. So as your sample size gets big, this approach tends to take longer and longer. So, and that's exacerbated for certain pockets of values for nu. Other people, so Ribeiro et al., use an asymptotic approximation of this normalizing constant to get a closed form estimate for lambda. But again, that doesn't perform well, especially when you have underdispersed data, and that's what I'm particularly interested in here. So it turns out that that polynomial I put on the previous slide has only got one real solution because it only has one sign change. So by Descartes' rule of signs, essentially we've got one positive real solution, and that's when R exceeds nu. So that helps life a lot. Only got one solution to look for, one real one. And that means we can solve the high order polynomial, but we've got to do that many times at each iteration. And we still have the problem that the polynomial is of infinite order, but we can get around both of these things. So the approach Alan Huang and I took was to basically pre-compute values for lambda based on choices of mu and nu on a fine-ish grid. So basically choose a mu, choose a nu, and work out what lambda would be by solving a polynomial. And we then use bilinear interpolation afterwards to basically finesse that estimate that we get. And it turns out that reduces computational times greatly. So you go from several hours to the order of minutes instead to fit the model, as I'll talk about later. And for us, we use a step size of 0.01 for both mu and nu. I chose mu to be in 0 and 19, so essentially I'm basically truncating that polynomial at 19. And the reason for that is you can't get more than 19 yellow cards in a game. So the problem of the infinite order polynomial goes away here because we have truncated counts. If you didn't, you could just choose some number that's twice as big as your largest observable count or something like that would get you most of the way. But here I have a defined upper limit, so I can't go beyond that. Nu, it's less so it's bounded below by 0. It could, in theory, go up to infinity, but values bigger than 1 indicate underdispersion. And in practice, I've never seen values bigger than kind of 2 or 3, so a value of 10 there is pretty conservative, but again, you could ramp up that value if you wish to. And basically, you can work out these values of lambda based on these choices of mu and nu, and you can use multiple cores on a standard MacBook. You can work out that lookup table in about 20 seconds. So that's a kind of pre-processing step that we do, and then we use that lookup table to fit our models thereafter. And this did well in simulation studies. So that encouraged me to fit a model. So we've got the yellow cards issued by the referee. Referee I to team J at home. Basically have a linear predictor for mu, which is what I wanted. So I like the model to have nice inferences, because hopefully other people will use it. What you don't want is a model that's got different inferences to what people are used to. You want people to take it up. So we've got some league effects, home advantage effect, an effect of the pandemic, the interaction of those two things, plus here some random effects for the referees and the teams as well. Also model dispersion at the league level, so I recognize that there might be more or less variability in a different sort of league. So the way the referees interpret the laws varies across the men's European football leagues. So in England, there's fewer yellow cards given historically than in Spain and Italy, for instance. And because the mean is different, that means the variation might also be different, so I model that separately for each league. Also model the dependency between the number of home and away yellow cards through a copula. And a similar approach has been used, so earlier reference here, model disciplinary points, goals in international soccer matches, and goals in English domestic soccer matches have also been modelled using a copula. In each of these cases, they used a frank copula, so I don't know how much people know about copulas. I don't know much. I basically learned about them for this bit of work, so I know a little bit more than I did 6 months ago, but I'm by no means an expert. But essentially, there's a range of associations you can pick from, and a frank copula seems quite a popular choice. It was either the only one used, or when people used a few, it ended up having the best AIC, or the best likelihood. So essentially, I used that one as well, spoiler alert. So I'm going to suppose y1 and y2 are random variables, so a crash course in copulas here. Last one slide, don't worry. A very famous reference by Sklar. Essentially, you can rewrite the joint distribution function f, can be written in this form here, where the copula is c. So c is a copula. Like I said before, there's many choices of copulas. And for Frank's copula, you get this explicit form. So here, u and v would just be the CDF for the distribution you care about. Yeah. So in this case, u here will be the probability of x is less than or equal to x, assuming we've got a Conway-Maxwell-Poisson marginal distribution. Same thing for v. Kappa is the term that defines the association. So if kappa is bigger than 1, you've basically got positive association or positive dependence. If kappa is less than 0, you've got negative dependence. So I should say in this model, we can also add 0 inflation at the marginal level or at the joint level. So you can augment the model in the usual way if you've got too many zeros. So the association is governed by kappa. And it's allowed to vary by league again, because we might think the dependence is different across different leagues. And we just use these mean parameterized CMP distributions as our chosen marginal. And I can still use a lookup table for the marginal distribution. I'm just now using cumulative probabilities rather than individual probabilities. And in terms of priors, we'll talk about the results. Basically use semi-informative priors for the league and referee effects, in that I didn't think a referee is going to give 10 times more cards than another referee. So the priors were constrained somewhat to think that, giving twice as many yellow cards might have a 5% chance or something like that. Vague priors for everything else, and sum to 0 constraints to place on the referees and the teams within each league. So doing this model around 10,000 MC iterations takes about 20 minutes, so far longer than a Poisson or negative binomial, but not terrible given the rewards that we hope to reap. So here's some results. So the posterior mean effect for being at home is 0.9. So essentially, teams that play at home get 10% fewer yellow cards, so 10% reduction in the rate. Likewise, playing behind closed doors, we get a 13% reduction in the rate. So during the pandemic, basically the rate of yellow cards went down by around 13% for whatever reason. And the interaction of these two tells something interesting. So essentially has an increase of 13%, essentially more than removing this home effect of 10%. So behind closed doors, the home teams on average got more yellow cards than the away teams. What we can't do is disentangle why that is, but it certainly seems that there's a crowd effect. Whether that means the crowd affects the referee, or the crowd affects the players, or a bit of both, I don't know. But we certainly see that the home advantage disappears when matches are played behind closed doors. The posterior intervals for the dispersions all lie above 1. And when nu is equal to 1, we basically we could reduce to a Poisson model. In this case, we at 95 posterior highest density intervals are all comfortably above 1, so we've got significant underdispersion at each league, basically justifying this model. Few, said I, after several months of working on it. The posterior HGIs for kappa all lie above 0, so that means we've got positive dependence within each league as well, so it was worth fitting this copula type model too. So everything has gone kind of to plan. These are box plots based on that MC approach for the mean league effects on the left and the variance of the referees on the right. So as I said earlier, this is the Premier League. So this is the mean number of yellow cards on this axis, the league across here. Premier League has far fewer yellow cards given on average, whereas La Liga and Serie A, the hot-blooded Latins, I would say, get more yellow cards, or a different interpretation of the rules. But that's not mirrored in terms of the referees. So what you'd normally find in count data is that the mean goes up, the variability goes up. So you commonly find underdispersed data when you've got small counts, because there's not much room for them to have a lot of variability. Whereas when you start talking about large values, then you usually get much more variability as well, right? So the two things go hand in hand. So you might expect the Premier League referees with the smallest mean to have the smallest variability, but they don't. What we actually find is that League One, French league here, which is third here, has got a much narrower band for the referees. And this isn't to do with the amount of data we have for each referee. They're broadly equally split, except Serie A, which has far more referees for reasons I can't fathom. all four are quite in keeping, except League One is quite a bit lower. So it seems like the referees in the French league seem more consistent in some sense than the other big 5 leagues. So these plots are not supposed to interpret individual points, they're supposed to give an idea of the shape of things. So here it's the posterior mean referee effects and the team effects. So we've got the posterior intervals for our referee effects on the left-hand plot, on our team effects in the right-hand plot, ordered from smallest to largest. So anything in the bottom left here is basically got a multiplicative effect that's making less yellow cards. Anything in the top right means more yellow cards. And essentially the spread is quite similar both for the referees and for the teams. So even though we think teams should be different and referees in theory should not be different, what we actually find is they're actually very similar in terms of their spread. We can also look at kind of top and tail was a nicer way of saying best and worst referees, or I guess most overzealous or less overzealous. What we see here is that the top referees kind of give out around 20-25% more yellow cards than the average referee. A lot of English referees in there. And then at the bottom we see these referees, quite a few from the Bundesliga, giving out a lot fewer yellow cards. I did look at Mr. Hernandez and hoped he looked kind of very, very sinister and stern or had an interesting backstory, troubled childhood, but no such luck, just someone who likes giving out yellow cards. Mike Dean's quite famous in the UK for being someone who likes to give out yellow cards like confetti, recently retired, but it's quite pleasing to see that borne out in the analysis here, that what people perceive to be the truth about Mike Dean came out in the wash. A bit more interesting for teams. Teams have more of allegiance people have more of allegiance to teams than they do to referees, obviously. Looks like Bill Shankly's words had the right effect. Liverpool get fewer yellow cards than any team in the Big 5 once you adjust for who they're playing, who the referee is, COVID, all those covariates. There's other things I could obviously put in the model, but as it stands, Liverpool are a team that get fewer yellow cards. What we might see is that these are largely successful teams down the bottom, so there's obviously some sort of relationship between success. Success normally means you have a lot of the ball, the way teams play at the minute, so a lot of possession-based teams. If you've got the ball a lot, then you've got fewer opportunities, often less need to commit fouls. So those two things kind of go hand in hand, so I wasn't that surprised by seeing these teams here. It's not always the case at the other end, though. It's not always the teams at the bottom of the league. It's often teams in the middle, or so on and so forth. Apologies if there's any Paderborn fans in the audience. I think I'm probably safe. So we see some teams here that, really get a lot more yellow cards, and that might be how they play, or something like that. A fan of these teams, so I know a Leeds fan quite well, and she thinks it's definitely some sort of referee bias against her team. But fans are a funny bunch, aren't we? We always perceive injustices, whether they're true or not. So I did a bit of model checking as well. So this is just basically some simulations from the model. So this is for the home yellow cards. This is for 0 yellow cards, then 1, then 2, then 3, then 4, then 5. This is just from the model, simulated 1,000 times how many yellow cards I'd predict, the probability of 0, and these blue dashed lines, quite hard to see, sorry. That one's better. They should sit somewhere in that distribution if the model is doing the right thing. And it seems most of the time here that the model is capturing the shape of this distribution quite well. Same thing for aways. Again, 0, 1, 2, 3, 4, 5. Doesn't seem quite so well for 3 away yellow cards and 5 away yellow cards, but as an overall picture, the model seems to be capturing the variability quite well. And what I should say, when I did this under independence, the model checking looked a lot worse. It missed things quite a lot more. So just to wrap up, so I've looked at yellow cards, but I would argue that the CMP mu distribution could be applied in lots of other places. So I did a brief bit of work on this over the last few weeks just to try and give a bit more of a US context. So just by chance, I looked at the Boston Bruins first and their data from last season, and they scored a mean of 3.72 goals, and the variance attached to that mean was 2.35, so under-dispersed data there. And also for their goals conceded, a bit closer now, but we have a mean of 2.16, and a variance is ever so slightly smaller of 2.09. And this kind of ties in with a few things I've seen. So often, Poisson distribution will work, except at the top and tail of a distribution, you'll often see less variability. And what you might see if you took the difference in teams, then you wouldn't capture the spread right if you used a Poisson distribution. Also, lots of other counts, baseball at the player level, lots of categories there. Small counts might have under-dispersion. NFL touchdowns at the team level and quarterback level, again, small counts, liable to under-dispersion. And rushing yards per carry by a running back as well. Thanks, everyone, for your time, and I hope you enjoy the rest of your day.